Okay, hello students. In this video, let us look into the next biasing circuit, which is considered or which is called as two supply emitter bias circuit. Okay, two supply emitter bias circuit. So we call it as TSEB, two supply emitter biasing circuit. Okay, so this is also an emitter biasing. You know, all this falls in the family of emitter, common emitter configuration. Okay, so keep that in mind. Now, why it is called as two supply? Why the name two supply is given? So, if you see the circuit, one supply which is given to the collector terminal, which is VCC, and normally in the previous biasing circuits and all, we saw that the emitter was connected to ground directly, right, through a resistor, RE. So in this biasing, we are able to see that the emitter resistance is not connected directly to ground now. It is given to another supply, which is VEE. Okay. Now, this is the biasing circuit which is normally used to design an op-amp. Now, if you see the op-amp, you know, op-amp means it is an operational amplifier. So if you say op-amp, OPAMP, later we will see, different feedback circuits using op-amp, operational amplifier, operational amplifier. So in the market, if you ask an op-amp, you will be able to get an IC for a op-amp. Okay. So you will have an IC for op-amp, which is normally called as MUC741. So this IC, normally, I am not going to write any pin diagram, later we'll discuss that, but here we'll have always in op-amp, we'll have two inputs and one output. Okay, so for an op-amp, you see, you'll have two inputs and one output. Okay, these both are inputs. The op-amp will work on two supply. One is plus VCC and another one is minus VEE. So when you say an op-amp, okay, when you say an op-amp, what type of configuration in op-amp is used? That configuration is nothing but whatever we are discussing now, which is two supply emitter biasing. So later stage, if I discuss on op-amp, and if I try to write the op-amp circuit in this way, you people should imagine that you have seen this video where a two supply emitter biasing circuit was being discussed. Okay. So anyway, brief about op-amp and all. Let us look into that later stage. But let me discuss about this two supply emitter biasing circuit and how how can we make this IC and VC values to be generated so that we can generate a proper Q point for this biasing circuit to work and also to be an independent of any sort of problems that by the PJT transistor occur while amplification. Okay, so this particular two supply emitter biasing circuit, I'm going to write this in a different sense now. I'm just elaborating the supply VE here. So let me take VCC here, and which is connected to RC. Okay. I'm just writing the loop diagram here. That is what I'm trying to do. So that while writing the equation, you will not get confused. Now this is your transistor, and I have an RE here. Okay. And then I have a base resistor which is connected to ground in this particular biasing circuit. Now what I'll do is I'll try to elaborate this VEE which is connected here. This is normally minus, okay, keep that in mind. This value of VE is minus and VCC is always plus. Okay, so if I elaborate this diagram, what I'll get here is I'll try to replace this with a proper battery which is VE power supply, and this is the base which is connected to ground like this. I can also say this VCC, instead of writing like this, I can also create a loop for VCC here. Now I'll take from here and connect the VCC and this. Okay, so this is your RB, RC, RE, okay, and this is your VE, and this is VCC. Now you need not to write plus VCC or minus VE here. Here, negative is given to the resistor, emitter resistance, and positive is connected to ground. Okay, positive is connected to ground, whereas negative is given to RE. So once we connect positive to ground, by default, this value of this particular voltage supply will be negative. And here you see positive is connected to RC, whereas negative is given to ground. So this value will be, normally positive polarity, because negative, when we give a power supply negative to ground, then the polarity of such source will be positive. When I give positive to ground, then the polarity of that particular supply will be negative. Okay. Now what we do is we'll try to write set of equations by looking into this diagram. Okay. So if I go with VC, now we will also mark this is VC, this is your V, and at this stage I'll get VB, and between these two is, which is VCE. We all know it. Now when I say VC, we can still, put the same equation what we did in the previous biasing circuit. VC will remain to be, VC will be remain to be equal to the total voltage VCC. I did not mark the current. Let me mark the current values. Now this is your IC, which is flowing through RC, and this is your IB, and this current, which is your IE. Okay, IE. So as usual, like how we wrote earlier for VC, now VCC, which is the total voltage, minus this remaining voltage is ICRC. So VCC minus ICRC is the actual equation for my VC. Okay. Now what I'll do is I'll try to write a loop equation now for this loop. Now we have a loop here and we also have a loop here. So I'll just write the loop equation for this particular loop. If I try to write the loop equation for this loop, what will I get here is, I can say it is minus IBRB. Okay, and we all know between this terminal we have one more voltage which we discussed earlier, which is VBE. Okay, so minus VBE minus IERE plus VE equals 0. So what I'll do is I'll try to write here again. We can rewrite it as VEE minus IBRB minus VBE minus IERE equals 0. So this is what the equation we got within this particular loop what we wrote. Okay. Now what I'll do is I'll keep my VEE. What is the requirement that we need, which I told you already, is I need to write an equation for two things for Q point. One is VCE and another one what I need is IC. Okay. So therefore, for VCE, we know that already we wrote this equation earlier. We know VCE is equal to VC minus V. And already I wrote for VC already. So let me see what is V, okay, which is voltage across the emitter. Now here, before doing that, let me derive this equation now for IE. Now if I write IE and IB, IB in terms of IE, so what will I get here is, I can say IB is equal to IE by beta plus 1. This we wrote earlier. If you remember the previous biasing circuit, this equation was written. So IB can be written as IE by beta plus 1. So I'll try to write that now here. So I can say it is VE minus VB. I'll keep these two in the left hand side. And I'll take these two terms, IERE. Now I can say added with IBRB, I can write it as IE by beta plus 1 into RB. Okay. Now what I'll do is, in both the equation, both the terms, I'll try to take IE common. So I'll take IE common here. I'll be getting RE plus RB by beta plus 1. RE plus RB by beta plus 1. And the left hand side will remain as it is, which is V minus VB. Now your IE will now be equal to, with this I can say my IE equals V minus VB divided by RE plus RB by beta plus 1. Now if you see this equation now, I can say for, anyway, IE is approximately equal to IC, so I got IC here now. In this equation, if I want the entire current IC to be independent of the temperature, okay, and beta variation, what I need to do is I need to make sure that, like earlier, what we did for 2 voltage emitter bias circuit, in this circuit, we need V to be very greater than VB. That is one thing we need to keep in mind. And my RE here should be very much greater than the value RB by beta plus 1. So with these two conditions, I can make IC to be independent of the temperature increment. So in this case, the numerator and denominator of this equation, okay, when V is very great compared to VB, I can say it is just V divided by, if RE is greater than RB by beta plus 1, I can approximate the denominator as RE. So therefore, now the emitter current of this circuit is completely dependent on two values. One value is the supply voltage VE, and the other value is the emitter resistance RE. If you are able to find out these two values, if you are able to fix these two values, you can make IE to be independent of the temperature and the variation in terms of beta value. Now coming to VEE, now I'll go back to the same circuit. Now coming to VE, the V voltage is this, okay. If I replace this circuit, write that circuit in externally like this, this is your circuit which is connected to ground, and this is your V, this is your V, from here to here is your VE, okay, whereas this supply is VE, and this is my RE, and the current flowing through RE is I. Now let me take this is plus and minus. Now if I try to write the loop equation for this, IERE plus VE equals 0. I can easily say now that VE equals IERE minus VE. So therefore, in this equation now, if you see, I am able to get the value for V. This is the equation where I can generate the solution for V, and this is the equation where I can generate the value for Vc, and therefore finally I can generate the value for Vce, which is Vc minus V. And with this equation, I can also generate the value for IC or IE, because we know that IE is approximately equal to IC. This is also equal to IC. So with these two values, finding out V, Vc and Vc and IEC, we can easily generate the Q point, which will have the value IC and Vc. I hope now you are clear with the terms of all this, whatever the value that we found. I hope you understood what is two supply emitter biasing circuit. Thank you.